This lecture is going to be all about matrices. So in particular, how do we think about a matrix, and what are all the various mathematical operations that we can do with matrices? Okay, so to start off, I just want to ask the question, what is a matrix really? Okay, not just what is it mathematically, what's the definition of it, but how do you think about a matrix? And so here's how I think about a matrix. So an n by m matrix, n by m matrix. So these are the dimensions of the matrix, but which one is which? So the first one signifies the number of rows, and the second number signifies the number of columns. Okay. So an n by m matrix, what it does is it encodes a linear transformation. Let's call it T. So T is not the matrix, T is the transformation. And where is this going to go from? What space to what space? Well, I always have to write it out to figure out where it's going to go. So this is a source of endless confusion. Let me draw a matrix. I'm going to draw a matrix with n rows and m columns. So I'll make it look rectangular, not too square. Okay, so we have n rows, and we have m columns. So in this example, m is less than n, but it doesn't have to be. Okay, remember the way a matrix encodes a linear transformation is this way. So we have a column vector here, and the linear transformation is the matrix times the vector. Okay, that's how you can implement the linear transformation. Okay, well this vector contains the scalars, for the columns, so this vector has to have length m. Okay, so this is a length m vector. And then what is this going to give me when I multiply this vector by the matrix? I'll get some combination of the columns. So that will be a length n vector. Okay, so I have a length n vector. Okay. So our transformation is going from our m, we're taking a length m vector, and we're spitting out a length n vector. Okay. And as you can see, it's a reverse order here. So this is a source of a lot of confusion. But I like to think about it this way, just by writing out the equation. What else did we learn last time? We learned that the columns of this matrix, so what are they? You have a bunch of columns. What do the columns represent? Well, what is this first column? This first column is T of E1. It's where our linear transformation sends the first basis vector. Remember, E1 is just 1 followed by a bunch of zeros. So it has a 1 in the first position. That's what the 1 indicates. And this is where the transformation sends the second basis vector. This one at the end would be where it sends the mth basis vector. Okay. Let's just do a quick example. I want to put some numbers in here. So multiplication by the matrix. Right, so it's matrix multiplication that represents multiplication of a matrix by a vector that represents the linear transformation. So what about this matrix? I have 0, 1, 4, negative 1, 1, 0. What is this? What transformation does this represent? So it's a linear transformation from what space to what space? Okay, well the input is going to be length 2, right? This vector here. So we'll go from R2 to R3. Because again, the output will be a linear combination of the columns, and we have 3 entries in each vector. Or you could just memorize this. You have to keep a lot in mind, right? So the first one is rows, the second one is columns. So we have a 3 by 2 matrix, so it will be a transformation from R2 to R3, right? What else do we see? We see that the vector 1, 0 goes here to 0, 1, 4. Okay? And we see that the vector 0, 1 goes here to negative 1, 1, 0. Okay? Okay, so here's a special case. An n by n matrix, that is same number of columns as rows. What does that represent? These are special transformations. It represents a transformation, a linear transformation, I should say. So a linear transformation from Rn to itself. Okay, and I want to give you one example of that. Here's actually a special example. So consider the transformation I'll just call it ID from Rn to Rn. And this is going to be a pretty boring transformation. It's just going to send every vector to itself. Okay. Is that a linear transformation? Well, what do we have to check? We have to check the properties. But those properties, once you write them down, you'll see that it's just obvious. Because this is sending every vector to itself. In particular, it sends the 0 vector to 0. And what are our properties? So T of v plus u has to be. Remember, we do need all of these. We need both of these properties in order to call it a linear transformation. This is a linear transformation, and we need that T of c times u is c times T of u. Okay, but yeah, these are both true. It follows right away. And I want to ask, what is the matrix associated with this transformation? So what is the matrix? With this transformation? Okay, let's try to draw the matrix. So it's going to be a square matrix, first of all, right? N by n. N rows, n columns. And what I put in the first column here has to be where the vector 1, 0, 0, 0, 0, 0, 0 gets sent under my transformation. Well, that's easy. It just gets sent to 1, 0, 0, dot, 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 all the way down to 0, right? The second column is where the vector 0, 1, 0, 0, 0, 0, 0 gets sent. That gets sent to itself also. Okay, and then the third vector will be this one, etc. until I get to the last vector. This column here has to be where 0, 0, 0, dot, 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 1 gets sent. But I'm just writing that vector itself. It just gets sent to itself. And so you see we get 1s down the diagonal, 0s everywhere else. This is called the identity matrix. Identity matrix. So it's the transformation that doesn't do anything. Okay, it's represented by this matrix with 1s down the diagonal, 0s everywhere else, and it has it's denoted I, capital I. Okay, so when you see capital I, that means the identity matrix. Okay, great. So next thing I'd like to talk about is, what if we have two linear transformations And we'd like to do one after the other. So this is going to be composition. It's like function composition, right? Composition of linear transformations. And this section actually has a secret title, which is matrix multiplication. But I'm not supposed to say that yet. Matrix multiplication is actually just composition of linear transformations. Okay, well, in any case, let's start with some linear transformations. So suppose that I have, let's make it explicit. So we'll go from R2 to R2. So we have T1 from R2 to R2. And we have T2 from R2 to R2. I'm going to start with all the spaces being the same. Suppose these are given by the matrices. So T1 of a vector, that's actually implemented as some matrix, we'll call it A times our vector x. Okay, and T2 will be implemented as a matrix B times my vector x. Okay, so multiplication by A, this one's multiplication by B. And here's the question I want to ask. What matrix corresponds to the composition I can do these in any order. Let's say I do T1 first and then T2. So here's T1, then T2. Remember when we write function compositions, this is the one that we do first. Do T1 first, then T2. Okay. So I want to figure out how to write down the matrix for this composition of two linear transformations. Surely it should have a matrix because it's itself a linear transformation. That's another thing that you'd have to prove, that the composition of two linear transformations satisfies these two properties still. But it does. And so if this is a linear transformation, we like to write down this matrix. How do we get that matrix? Well, let's think about this. So what is this doing in terms of these matrices? So I'm applying so let's say I want to apply T2, T1 to some vector x. Okay. Well, what is that? It means I apply T1 first. Okay. And then I apply T2. But what is T1? T1 is the matrix A times x. And then T2 is B times whatever this is, right? Right? T2 of x is B times x. I have a vector. This is a vector, right? A matrix times a vector is going to be another column vector. So this one will be B times A times x. Okay. So let's write this down. Actually, let me get another piece of paper. This is actually going to be super important, so I want to do this as clearly as possible. Let's write the matrix B and the matrix A. So they're 2 by 2 matrices. I'm actually just going to put in letters for the entries. So A, B, C, D. There's my matrix B. Okay. And here's my matrix A. E, F, G, H, like this. Okay. I'm doing A times my vector x. So let's call it xy. Okay. I want to write down the matrix for essentially the product B times A. We haven't talked about matrix multiplication yet, but I'm going to try to write down the matrix for this product just by thinking about the linear transformations. Okay. So that's what I'd like to do. We'd like to write down a single matrix for this linear transformation. And whatever that matrix is, that's how we'll define the product. Okay, because that matrix should be B times A. And again, I'm not going to tell you how matrix multiplication works. I'm not going to say, this is how you do it and memorize this rule. We're actually just going to figure it out together right now, just by thinking about a linear transformation. So how do I write down the matrix for a linear transformation? I think about where the basis vectors go. So that's my question I'm going to ask. Where does this vector go? 1, 0, and then I need to do 0, 1. So where does this go under my linear transformation? Okay. Well, this is the matrix implementing T1, right? So where is this vector going to go under this transformation? Can you see right away where it's going to go? It's going to go to EG, right? Because that's what this column represents. So T1 of 1, 0 is going to be EG. Okay. Well, then what is T2 of EG going to be? Well, that's going to involve a little more calculation, right? So it's going to be this matrix here times EG. Okay. So I just did T1, now I'm going to do T2. So I need to multiply by this matrix B. So it's going to be E times my first column, right, just by our definition of matrix times a vector, plus G times our second column. And this ends up being the vector AE plus BG, and then CE plus DG. Okay, so this is getting a little bit complicated. What about the other basis vector? So where does 0, 1 go under T1, under my transformation? Sorry, this should be T1. Well, this is what the matrix for T1 is, so it should go to FH. So that's what happens to 0, 1 under T1. Now I have to apply T2 to that. So what's T2 of FH now going to be? Well, it'll be this matrix times this vector, which we can just write it out more quickly. AF plus BH is going to be that first entry, and then CF plus DH. Okay. Well, what does that mean? Then the matrix for doing T1 followed by T2, B times A, should be what? What do I put in the first column? I put where 1, 0 goes. AE plus BG, and then CE plus DG. And then what do I put in the second column? I put where 0, 1 goes. AF plus BH, CF plus DH, like that. Okay. And you might recognize these formulas. You've probably learned these formulas at some point for how to multiply this matrix times that matrix, right? But we actually just derived these formulas from scratch just by thinking about, again, interpretation of matrix multiplication as composition of functions. Okay. And so how does this actually work? If we look at this formula right here and say, well, how do you get that from these two matrices? So it looks like it's A times E, okay, plus B times G. So you're sort of going across this first row, and then you're going down the first column, right? So it's A times E plus B times G. And then what's this? A times F plus B times H. You're going across the first row, and you're going down the second column. So you're doing A times F plus B times H. Okay? And then similarly for these entries, you're using the second row this time. And so in general, how does this work? So in general, let's suppose I have two matrices. So how do I want to do this? Okay, so a k by n matrix. I need 3 letters. Times an n by m matrix is, well, what is it? Let's write this out. Okay, so here's my first matrix, and then let's have be a taller one like this. I think I have too many rows in this one, or too many columns in this one. So I'm going to remove a column. Okay, so I have a k by n matrix. Times an n by m matrix. Okay, so this is n. This is m. What should that be? Okay, well, let's just think about it in terms of linear transformations. This is a linear transformation from, where is it starting? Think of your vector being multiplied on the right. That vector should have m elements, right? So it's going from Rm to Rn. That's what the first matrix is doing. And then I'm going to multiply by the second matrix. So now I have a vector in Rn, and I'm going to Rk. So what matrix should I get? I should get the one that goes from Rm to Rk. So I should have m columns and k rows. So this should be a k by m matrix. So this is a k by m matrix. Okay. So this is again k, and then we have m here. How do I get a specific entry? So let's say I want this entry. How do I get the entry in, let's say, row I, column j? Well, here's what you do. You take row I of the first matrix. So do this in another color. So I take row I, let's say. This is row I. And then I take column j. That better be the same number, right, of entries, n. So this is column j of the second matrix. And then I do this one times that one, plus this one times that one, plus that one times that one, etc., all the way down the line. And then whatever I get, that huge sum is just going to be that entry right there. It'll be row I, column j of my resulting matrix. Okay, that was probably a little bit confusing. I think it's time to do a numerical example. Let's multiply two matrices. And again, you might have done this before, but just want to make sure we're all on the same page here. So I'm going to multiply this matrix by this matrix. And I think it's good to see where these formulas come from also. These aren't formulas you necessarily just have to memorize. They just come naturally from thinking about matrix multiplication as linear transformations, as composition of linear transformations. Okay, so how do I do this? Well, what's my first entry going to be? Row 1, column 1. It's going to be row 1 of the first matrix times column 1 of the second matrix. But here's what I have to do. I have to do 3 times 0 plus 2 times 1 plus 0 times 4. And then this entry over here is going to be 3 times negative 1 plus 2 times 1 plus 0 times 0. This entry here will be negative 2 times 0 plus negative 4 times 1 plus 1 times 4. And then this one here will be negative 2 times negative 1 plus negative 4 times 1 plus 1 times 0. Okay. And what do we get in the end? So yes, as you can see, this is a complicated process, but we get 2, -1. This looks like it's just going to be 0. And then here we have 2 minus 4, which is -2. Okay, so we get this matrix. And notice it is a 2 by 2 matrix. Is that what we expected? Okay, so here K is 2, right? N is 3, and then M is 2. Yes, so we are expecting a 2 by 2 matrix. One other thing to note, see this number here? That had better be the same as that number here. So I'll just say that. So these numbers, notice K does not have to be the same as M, but these inner numbers here, these numbers have to be the same. If they're not the same, you can't multiply the matrices. It's not even defined, right? But I want you to note something, which is this does not maybe work the way you'd expect it to work. So, and there are several weird things going on. So let's say if A is a 2 by 3 matrix, and if B is a 3 by 2 matrix, well, what is AB going to be? And what is BA going to be? Yeah, without even calculating it. Okay, so 2 by 3 matrix times 3 by 2 matrix is going to be, so first of all, I have to make sure these match, right? But they do. It's going to be a 2 by 2 matrix. But then B times A, 3 by 2 times 2 by 3 is going to be a 3 by 3 matrix. Okay, so that's a little bit weird. A times B, not necessarily the same as B times A. It could even be a totally different size matrix. Or, even worse, it might not even be defined. What if I did that one times that one? Well, the M doesn't match up with K, so that's not even defined. Okay. So I think it's time to talk about a few properties of matrix multiplication. So properties. First property is that matrix multiplication is associative. What does that mean? That means if I have a bunch of matrices, let's say 3 matrices, it doesn't matter whether I do A times B first or whether I do B times C first. Okay? As long as I keep them in the same order, that's key. And why is that? It's because what is this representing? This is just representing a bunch of linear transformations. So let's say I'm going Rm to Rn to Rk, I need another one, I think, to Rl. Okay, so C is actually the first transformation, right? This is confusing. The matrix on the right is actually the first linear transformation being applied, and this one corresponds to B, this one corresponds to A. Okay. And what is this saying? It's just saying if I do A and a B, right, together as a group, or sorry, I should say the other way around. I'm starting from this side. It's saying if I do C and then B and an A, that's the same as doing C and then B and then A, right? Everything's just going along this line. There's really no content to this. Matrix multiplication is associative. It doesn't matter what order you group the matrices. But by the way, this would be terrible to actually try to prove using symbols like we did up here. But thinking about it in terms of transformations, we just immediately see that it's going to be associative. However, it's not commutative. So, but it is not commutative. And commutative means that AB equals BA. That's not true. So I'll put a not equal there. And so here's an example. So let's take matrix A to be I want matrix A to be a 90-degree rotation counterclockwise. So how do I do that? So this is a 90-degree rotation counterclockwise. I'm going to try to figure out two linear transformations where if you reverse the order, you actually change the outcome. Okay. So I don't want to do another rotation for B because it won't really matter what order you do those in. I want to do something different. I want to do a flip across the y-axis for B. And hopefully, if we do the rotation then the flip, that'll be different than the flip and then the rotation. You might not be buying that, but let's first write down the matrices. So what would a 90-degree rotation counterclockwise be? Well, where does 1, 0 end up? It will end up at 0, 1. And then where does 0, 1 end up? That's why I put in the second column. It will end up at negative 1, 0. See how quickly we can write down linear transformations just by thinking about the action on the basis vectors. And then how about B? What if we flip across the y-axis? Well, then 1, 0 is actually going to negative 1, 0. And 0, 1 is just staying as is, right? So it's this. And now, let's multiply these matrices out. So AB, well, what's that going to be? It'll be this matrix times this matrix. And remember, what is the meaning of this one? This one is actually doing the flip first, right? This is the flip, right? So I'm doing the flip first, then the rotation, if I'm thinking about the linear transformations. You should try to multiply these out for practice too. But I'm going to write down what it is. So that should be 0. This should be minus 1. This one's going to be minus 1. This one's going to be 0. So that's what we get. This represents the composition of doing the flip, then the rotation. And this one will be the rotation, then the flip. Okay. And here we get, hopefully, something different. This is going to be a positive 1, right? Negative 1 times negative 1 plus 0 times 0. And this will be a positive 1, and this will be 0. So see, we get something different depending on what order we do these two transformations, which is really, really cool. I'd love to actually demonstrate this. I'm just trying to see if I have an object that... Oh, perfect, actually. So I've got a pack of cards here. So let's take out the ace of spades, maybe. Actually, this back is you can't really tell which way is which. So let me use the whole pack, actually. Okay, so what am I going to do? Let's do the rotation counterclockwise, then the flip. Okay, so I'm going to rotate 90 degrees counterclockwise, then I'll flip. Okay. Now, memorize what this looks like. Okay. Now I'm going to do it the other way around. I'm going to do the flip, and then the rotation 90 degrees counterclockwise. So that's different, right? The logo is over here now. It was over there before. So let's do it one more time. So rotation counterclockwise, then the flip. Okay, logo is over here. But now if I do the flip, and then the rotation counterclockwise, it ends up over there. So that's a demonstration that matrix multiplication is not commutative. Okay, so we'll put that aside. Okay, what next? Well, I mean, I should just mention some other operations you can do. These aren't as exciting. But you can add matrices. The way you add matrices is just like this. So let's say I have 2, 0, 1, 4, 3, negative 2. And I'm going to add 0, 7, negative 2, 3, 0, 1. You just add component-wise. So 2. So see that 2 is just coming from 2 plus 0. And then just do 0 plus 7. So not as exciting as matrix multiplication, but we can add matrices. We can multiply by a scalar. So if I do 3 times a matrix, what do we want that to mean? Let's do a negative 1, or 1, negative 2, 4, 0. You just multiply all the entries by 3. So that's what that's going to look like. What else can we do with matrices? We can do something called a transpose of a matrix. And I'm not sure we're really going to go into this later in the course, but I just want to cover all my bases here. So if A is, let's just do this matrix 2, 4, 0, 3, 1, negative 2, then the transpose of A, denoted AT, is this matrix, 2, 0, 1, 4, 3, 2, 3, negative 2. How did I get that matrix? I just flipped across the diagonal. So that's how you get to transpose. The rows become columns, the columns become rows. What else can we do? We can take the power of a matrix. That's an interesting one. So that involves multiplication. Okay, so a to the kth power, you just write it like a normal exponent. The matrix is the base. Well, what do you think that means? That just means a times, sorry, there's not a plus sign there. It's all multiplication. Yeah, dot, 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 times a. And we're doing this k times. Okay. You can even do really crazy things, like you can do e to the power of a matrix, which is defined, probably the way you define that is by the Taylor series, but we're not going to get into that. So let's just talk about a few selected properties using these various operations. And really, so I'll just call it selected properties. Because I could probably write down 20 or 30 properties. Let's just say some of the most important ones. So here's a property. If you do A times B plus C, sorry, it has to be a C, that's the same as doing AB plus AC. So there's a distributive property for matrices. You can do that the other way around too. So if I have A plus B and I do C on this end, that's going to be AC plus BC. What else can we do? What if we do A times the identity matrix? What do you think multiplying by the identity is going to do? The identity matrix. Well, nothing interesting, right? Because if we think about it as transformations, we're doing the nothing transformation followed by A, which is just the same as just doing A, right? And we can do it the other way around. Doesn't matter. We can do the transformation A followed by the nothing transformation, but that's the same as doing A. What if we do A times 0? What do I mean by 0? The scalar 0? No, I mean the matrix 0. It's a matrix of all zeros. Usually this will be a bold 0, but it's hard for me to write bold. What does the matrix of all zeros do? That linear transformation actually just sends everything to 0, right? Because every column is just the all zeros vector. So all my basis vectors get sent to 0. So this ends up just being the 0 matrix. Okay. So I have sort of a 0 matrix. I have an identity matrix, which acts as the multiplicative identity. Okay. 0 is also an additive identity. So A plus the 0 matrix is going to be A. Same for the reverse. There's some properties about transposes. So A plus B, then take the transpose. It's the same as A transpose plus B transpose. And this one looks interesting. But when you write it out, it's actually, you find it's not that interesting, actually. If you do the product and then take the transpose, that's the same as taking the transpose of both pieces and then taking the product, but in the opposite order. So you have to multiply the other way around. But essentially, the reason that is just because, when you do the product, you're doing rows of the first one times columns of the second one. The transpose sort of turns the rows into columns and columns into rows. So in order to get the same product, you have to then flip the two matrices. Flip the order of the two matrices. What is A transpose transpose? Flip it across the diagonal, flip it back. So it's just A again. Okay, that's enough properties for now. Again, there are many more we can write down. Okay, the last part of this lecture should just be, we call this caution. Cautions. Because, again, this doesn't always work the way you'd expect it to. So we saw that AB is not the same as BA. So that should be our first one. AB is not the same as BA. Sometimes it is, but you can't guarantee that it is, right? In general, it's not going to be. Because of that, you get weird things like this. So what do you think A plus B squared is going to be? Well, here's what it's not. It's not A squared plus 2AB plus B squared. Okay. It's not true. However, it is true that A plus B squared, that does actually equal, you can write that as A plus B times A plus B, right? It's just the definition of the power, which is A squared plus BA plus AB plus B squared. But I'm saying that that's not equal to that? Well, no, it's not, right? Because look at what we're using to get from there to there. We're using the fact that AB and BA are the same, which is not true, right? So you have to be super careful when you're trying to carry over properties you've learned in algebra to matrix algebra, because they don't always work. You have to really keep track of which ones are using commutativity and which ones are not. Okay, some other weird stuff. So let's say I have two matrices and I multiply them together and I get this matrix of all zeros. Does that mean that A is equal to 0 or B is equal to 0? Well, it's in the caution section, right? So this does not mean A equals the 0 matrix or B equals the 0 matrix. Okay. Here's an example of that. You take A to be this matrix, 1, 1, 1, 1, and B to be this matrix, 1, negative 1, 1, negative 1. There aren't even any zeros in these matrices. But when I multiply them together, I get the all zeros matrix. Right. Again, right, how am I getting that 0 there? I'm doing 1 times 1 plus 1 times negative 1. That gives 1 minus 1, which is 0. Okay, that's not true. Here's another thing that's not true. So let's say I know that AC equals BC. This does not mean A equals B. And rather than give you an example, I'll leave this as a problem for you. This is a fun one to try. So problem, find matrices A, B, and C, just by sort of playing around with it, such that AC equals BC, but A is not equal to B. They're different matrices. Okay. And you can actually just do this all with 2 by 2 matrices. So try doing it with 2 by 2 matrices. Okay. All right. So probably end this lecture soon, but I can't resist just doing one or two fun problems. So the first one. These are just fun things to think about. So is it possible to find a 3 by 2 matrix, so 3 by 2 matrix called, let's call it A, and a 2 by 3 matrix, and this will actually foreshadow something we're going to talk about a little bit later. We'll call that B, such that A times B equals the identity matrix. Okay. Well, let's think about it. So what would A times B look like? So it's a 3 by 2 matrix. I have 3 rows and 2 columns. So there's A. Okay, so here are my entries. And I'm multiplying by B. I'm multiplying by a 2 by 3 matrix. So, and I want that to equal the identity. Well, wait a second. So what identity matrix should I have? Should I write the 2 by 2 identity matrix? Identity matrix is always square, but should I write the 2 by 2 identity matrix or the 3 by 3? Well, I'm multiplying a 3 by 2 matrix by a 2 by 3 matrix. So I just have to check, is 2 the same as 2? Yes, so we can multiply them. And then the result will be 3 by 3. Right? So this should get me the 3 by 3 identity matrix, which looks like this. Okay, 1's down the diagonal, 0's everywhere else. There's I, there's A, and there's B. Okay. So you could try to, play around with this. Try putting in some numbers, so you get a 1 there, and a 0 there, and then a 0 there. And you'll find that it's harder than it seems. And there's a reason for that. The reason is, let's view this as a linear transformation. So what is a linear transformation I'm applying first? I'm applying B, and B is a linear transformation from R3 to R2. Right? Imagine I have a vector on the right side of B. It has 3 components, right? So this is the transformation associated to B. I'm just going to write B, even though technically I should write like T or something. Right? It's a transformation associated to B. And this is the transformation associated to A. Okay? Here's a question. Is this onto? What do you think? Can this transformation be onto? Well, every vector in R3, I don't know whether TB is onto or not. It could be onto, this part here. But then every vector here is going to be sent somewhere in R2, okay? And then these vectors are going to be sent somewhere in R3. But look at this second transformation. I'm going from R2 to R3. That can never be onto. So this can never be onto. Right? That's something that we saw in the previous lecture. Okay? And again, the intuition is we're going from a 2-dimensional space to a 3-dimensional space. 2-dimensional space, you can't map to the entire 3-dimensional space. It's like you can collapse the 3-dimensional space down into 2 dimensions, but then you can't uncollapse it back. You sort of lose some information. So this can never be onto, which means that this entire composition can never be onto. Okay? So no, it's not onto. Because again, if I start here, where you're saying, well, wait, maybe I can start here and still end up hitting the vectors here that this one didn't hit. Well, no, because this one has to go through here, right? I'm doing this transformation first, going to this space, and then going back to the 3-dimensional space. So it's not onto, but this identity matrix represents an onto transformation. From R3 to R3. Right? It's also one-to-one. It's one-to-one and it's onto. You'll see it has 3 pivots. It's already in best possible form. So that means that I can never actually find A and B, 3 by 2 and 2 by 3, such that A times B equals I, because this one will represent an onto transformation, and this one will not represent an onto transformation. Okay. So that's a really tricky way to solve this problem. But again, you can. I hope you weren't trying too long to plug in numbers there and try to get this, because you can never get this matrix from 3 by 2 times a 2 by 3. Let's see. Do I have time for one more? All right, fine. Well, one more. So let's find a non-zero matrix A. Let's stick with 2 by 2, such that A squared is 0. That's crazy. So if I square a matrix, I get 0. Okay. So again, you can kind of play around with this for a while, and you'll probably figure it out without too much effort, actually, if you start writing down some matrices. They can't be the all zero matrix, though, right? I need at least one of the entries to be non-zero. But this one's also really fun to think about in terms of linear transformations. So like, can we design a linear transformation such that when you do it twice, it just sends everything to 0? But when you do it once, it doesn't? Well, let's try it. So what do I want to specify? I want to figure out where 1, 0, and 0, 1 go, where my standard basis vectors go. Okay. So here's what I'm going to do. I'm going to design this so that I try to design a linear transformation so that the first thing that happens is it's just going to collapse this whole x-axis into the 0 vector. Okay. So here's what I want my first column to be. I want 1, 0 to go to 0, 0. I just want to push it down to 0. And then, of course, any multiple of 1, 0 is also going to go to 0. So my first column will just be 0, 0. That's the image of 1, 0. And then I could say, well, let's keep this vector where it is. But you see the problem with that. If I do it twice, it's just going to stay there, right? Everything here already got collapsed in. Or this vector here would get collapsed into the y-axis, but then it's just going to sit there. I really want everything to get collapsed into 0. And so to do that, I'm going to do something tricky. Where do I want this vector to go? I'm actually going to send that vector to the point 1, 0. Okay? So you see what I'm trying to do here? So I'm collapsing in things this way to the y-axis, but then I'm sending the y-axis at the same time onto the x-axis. So then what's going to happen if I do this twice? Oh, I should get 0. Let's see if we actually do. I should just get the all 0 transformation, the matrix of all zeros. Okay, I get 0 there, and I have 0 times 1 plus 1 times 0, that's also 0. And then this is just a bunch of zeros. And then I have 0 times 1 plus 0 times 0, which is another 0. So I get the 0 matrix. Yet neither of these were the 0 matrix. Okay. In fact, this is a matrix where you square it, you get 0. And these have a name, actually. This is called a nilpotent matrix. Nilpotent matrix is one that you can raise to a power. It's a non-zero matrix, but you can raise it to the power and get the all zeros matrix. So, okay. So as you can see, matrices and matrix multiplication can be truly weird. But sometimes it's really nice. And so in the next lecture, we're going to talk about when it's especially nice, when you can actually invert a linear transformation. So we'll talk about invertible matrices. So I'll see you then.